Hello and welcome back to our channel. This video is all about gravity specifically. This topic is under Unit 3, but we wanted to give it a little more emphasis since, at least from our experience, a lot of people seem to struggle with it. Okay, so let's get started. So, gravitational force. So what is this gravitational force? So the definition is that this force pulls objects with mass toward each other. So what this means is that any massive object, and when I say massive, I mean an object that has some amount of mass, is always attracted to some degree to another massive object. Something key to understand is that this force acts as on the center of masses of each object, and they are acting on each other, meaning according to Newton's third law, they're always equal and opposite. So, for example, you pull on the Earth with the same force that the Earth pulls on you. Now, this might be a little strange to think about, but let's dig a little deeper into how we get this gravitational force, and then maybe you'll understand it a bit better. So, the gravitational force is universally calculated by this equation right here, Gm1 m2 over r squared, where G is equal to the gravitational constant 6.67 times 10 to the negative 11, and m1 is the mass of the object, m2 is the mass of the other, and r is the distance between them. Now, you might say, wait a minute, isn't it just mg? Well, yes, but it is that specific to objects that are close to the surface of the Earth. The gravitational acceleration g is simply derived from this universal equation. So if we equate this equation to mg, right, we can see that your mass, let's say m2 is your mass, let's say and then your mass canceled. And then that's how scientists approximated g right here. So g was equal to this gravitational constant times mass of the Earth divided by the radius of the Earth squared, right? Now, going back to the idea that you and the Earth are pulling on each other with the same force, when we look at this equation, right, we have your mass, the Earth's mass, and the Earth's radius. And if we equate it to the Earth's mass times acceleration, we see that the Earth's acceleration is basically negligible. So because the Earth's mass is so big, even though you do still apply an equal and opposite gravitational force on the Earth. Right, now moving on. The gravitational field. So this is different than the gravitational force. This actually essentially refers to the acceleration of the object in question that would experience in response to another object that is applying a gravitational force on it. So this is calculated by Gm1 over r squared, where m1 is the mass that is applying the gravitational force, and r again is the distance between them. Right, and in fact, g, right, the acceleration due to gravity on Earth, is calculation of the gravitational field near the surface of the Earth. So that's when m1 is equal to the mass of the Earth, and then r is equal to the radius of the Earth, right? So that's just an approximation. Moving on. So gravitational potential energy, right? So what is this? This is the energy an object possesses because of its position in a gravitational field, and is calculated by negative Gm1 m2 over r squared. So why is it negative? This is simply to show that there's an attraction between the two masses. We know that energy isn't a vector, so we can't assign directions to energy. So we simply say negative just to show that it's an attractive entity. And again, you might be wondering, well, isn't this mgh? Well, and again, the answer would be that this equation right here is the universal law, and mgh is specific to the Earth. And this gravitational potential energy is useful when considering things like escape speed or when applying conservation of energy. And we'll take a look at things like that later. So let's talk about mass dependent on radius and density. Right, so we have this equation, right, where density is equal to mass divided by volume, right? And so if we rearrange this equation so that mass is equal to, right, multiply volume on each side, and you get density times volume, right? So, and then the volume of a sphere, right, is 4/3 pi r cubed, right? So we can equate this, the density times 4/3 pi r cubed, right? gravity problems, most objects will be spheres. So this is reasonable to assume. And so the mass will be dependent on this density and this radius, right? And we have to be careful here because this radius doesn't always make up the entire distance between the center of mass of the two objects, right? So which is used to find the force of gravity, right? It can be part of it, but it isn't the whole thing, right? So, for example, you're at a point 10 kilometers above the Earth's surface, right? So if this is the Earth, and you're, say you're right here, right? So if you're right on the surface of the Earth, that means that you will use the radius of the Earth as the r in FG. However, if you're, like the problem says, 10 kilometers above the Earth, say right there, that's not drawn proportionally, obviously, but if you're 10 kilometers above the Earth, then your radius will actually be that, because your center of masses are that distance apart. So the r that you would use in this gravitational force equation would end up as radius of the Earth plus the 10 kilometers that you're above it, right? Now, moving on. Okay, so here's an example of the radius of the planet changing the mass. So there's a planet P1, let's draw it out real quick. P1 with mass density rho and radius r, right? And another planet P2, right? This is P1 with mass density 1/2 rho and 3r, so it's 3 times the radius and half the density, right? So find the ratio of gravitational field on the surface of the planets due to P1 versus that of P2. And if we remember, the equation for gravitational field is just simply g times the mass of the planet, so m1 over, right, the radius squared, right? And so if we're trying to find, if we find the gravitational field of P1, right, let's do that first. So now first we'd have to find the mass of P1, right? And this is where proportionality comes into play, right? So if you don't want to say calculate everything with the constants like g or like 4/3 pi, right? Then we need to take into account proportionality and see which variables are changing, and use those to set up these proportionalities. For example, right, if we have that the F of the force of, or not the force, the gravitational field is equal to, let's just say, this is A, right? A is equal to gm1 over r squared, right? So if we set that equal to each other, this means that A is actually proportional. This is the proportionality sign to m over r squared, right? And so what does this mean, right? So, well, m is equal to what? Rho times 4/3 pi r cubed, right? Because that's what we found earlier. And then we set that over r squared. And then we can just cancel that, right? Well, what if we don't want to account for this constant right here, right? Because they're not going to change anything, right? So then that means we can do A is actually proportional to rho times r, right? We can just get rid of this constant when we're accounting for proportionalities, right? So essentially what that means, right? So if we calculate the A, like proportionally calculate A for P1, right? That means we get, because so the mass density is r and the radius is, it's rho, sorry, and radius is r. That means A1, right? A1 is, let's say that's the gravitational field of P1, is actually proportional to the rho times the radius, which is r, right? And so if we do the same thing for P2, we get that A2 is proportional to 1/2 rho, right, times 3r, right? And the reason we can use these proportionalities to find this ratio is that we're finding the same value for both of them. In which case, if we were to take the ratio, all the constants would cancel out anyway. And so what we would be left with is what changed for each one. So what changed was rho and what changed was r. And so if we were to find the ratio, it would end up being the same, even if we did the whole calculation for the whole thing, right? And so now we can set a1 over a2, and that would equal, right? So the rho and the r would cancel, and so that would be 1 over, right, 3 over 2, right? And then that would just be 2 over 3, and that would be our answer, right? Now let's take a look at a different example where radius affects both the mass and the distance. So we have two identical spheres, S1 and S2, both of which have density rho and radius r are touching. So let's draw that out. So S1 and S2 are identical and they're both touching. So if the density of S1 is doubled and the radius of S2 is tripled, what is the ratio of the force between them before versus after alteration? Right, so this one is S1 and this one is S2. So what does the force of gravity depend on? So let's write that out. So F of G is equal to G m1 m2 over r squared, right? And so from there we can say that the force of gravity is proportional to m1 times m2 over r squared, right? And now we have to take a look at how m1 changes, how m2 changes, and how r changes, right? So let's first take a look at r, right? That should be pretty simple. So it says that, so the radius of S1 stays the same, right? But the radius of S2 is tripled, like this. And since this r right here is the distance between the center of masses of these two, right? We can just find this distance right here, right? So this is 3r, right? Because we tripled it, and then this right here is just r, right? And so the distance, this one, is actually just 4r, right? And then now let's take a look at the masses. How did the masses change? So m1 changed because the density of S1 is doubled, right? So what is mass proportional to? Mass is proportional to, like we said before, the density times what is it? The r cubed, right? Because the volume of a sphere, right? And so the r isn't changed for S1, but the density is doubled. So this means that this is proportional to 2 rho r cubed, right? And so that would be, so basically the mass is doubled, right? So we can just say times 2 for here. And we don't really have to worry about what doesn't change, like the r, right? And so now let's take a look at m3, right? What is m3? M2, sorry. So how did m2 change? So the radius of S2 was tripled. So this means that, let's clarify this. So m2 is proportional, which was proportional to rho times r cubed, right? And so rho didn't change, so therefore that's proportional to rho times r 3r cubed, so that would be 27 r cubed. And so this mass right here was multiplied by a factor of 27, right? And so what we're looking for is the ratio of the force between them before versus after alteration. So if we find what this after alteration force is, right, it's just, we don't have to worry about any of this. We're just worrying about how it changed. So it would be multiplied by 2, multiplied by 27, and then divided by, right? There's 4r here below squared, so it would be divided by 16, right? So that's basically, well, and then times m1, m2 over some r squared. And then, well, we're not done yet though, right? Because we need to find what was the force before the alteration, in which case that one was just, what, m1 times m2 over, the distance between these two was actually 2r, so that would be 4, right, r squared, right? And so this is the force before, and this is the force after, right? So the ratio of the force between them before versus after would just be this one divided by this one. So, well, the m1, m2, and then r squared would just all cancel, right? And then we're left with a number. So it would be 2 times 27 over 16, right, over 4, which comes out as, what, 54 over 64, right? And then that's your answer. Now, let's take a look at orbital speed. So, the equation for orbital speed is equal to v equals root gm over r, where m is the mass of the object being orbited and r is the radius of the orbit. So, let's derive this, right? So, what we're saying is that if there's a planet, with, let's say a planet with mass m here, and we're orbiting it at some radius, right? And so let's say this is center of mass, and let's say this radius is r, right? And it's a circular orbit, right? It has to be circular orbit for you to calculate this, right? So let's find the forces on this object right here, right? So if an object is, let's say, at that point, let's say this is the object, right? The force of gravity pulls this way, right? And that's the only force that's acting on the object, right? Well, and this seems a bit familiar, doesn't it? Because, like, well, it's in a circular orbit, and there's a force acting toward the center of rotation. Well, what is that force called? Well, that's basically the centripetal force, right? And what is the calculation for centripetal force? Well, that's mv squared over r, where m is the object that's doing the rotating, right? And so, well, let's set those equal to each other. Fg, right? Fg is equal to g times m1, m2 over r squared. And then that's equal to, right, mv squared over r. And these r's are equal, right? Because that's the r of rotation, and this is also the r of rotation, so we can just get rid of that. And then what is this m? We can just, let's just say that m2 was the mass of the object that's rotating, and then this m is also the mass of the object that's rotating, so we just cancel these two. And what you're left with is that v, right, if we solve for v, you just square root both sides, is the root of g m1 over r, right, where m1 is the mass of this planet right here. And so that's how you derive the orbital speed. And we'll take a look at an example later on. So escape speed, right? So the equation of escape speed is a little bit different. So this is actually the root of 2gm over r, where m is the mass of the planet you're trying to escape, and r is the radius of that planet. So how do we derive this? Well, let's take, for example, a planet, right? And you're on the surface of the planet, and you're launching yourself with a certain velocity. And your goal with escape speed is to escape the gravitational field of this planet and just make it out, right? So what does that mean? It means that it's basically will be infinitely far away, right? With zero speed, or yeah. And so the U are over here, or the potential energy, would be 0 because it's infinitely far away. And then the K, which is the kinetic energy, would also be 0. That's your goal, right, with this. And so, what is your initial energy here when you're launching yourself? Well, first you have U initial, which is what negative, right? Don't forget the negative. Negative G M1 M2 right over R. And then what is your kinetic energy, right? Well, that's K is equal to 1 half, right? Let's specify this M. So let's say this mass of the planet is M1, or it's supposed to be M, but let's say it's M1, and your mass is M2, right? So M2, and then certain V. That's what you're trying to find, right? V escape. I'll just write VE squared, right? And so using conservation of energy, right? UI plus KI has to equal, right? What this final U plus final K, which is equal to just 0, right? And so essentially what you're saying is that this negative GM1 M2 over R is equal to if we move it to the other side of the equation, it would be negative 1 half M2 VE all squared, right? And then the negatives would cancel, which would mean that basically these two are equal if we get rid of this negative sign right here, right? And so what you have here is that GM1 M2 over R is equal to 1 half M2 VE squared, right? And then we can just cancel out the M2's, right? And then multiply both sides by 2, so that, and then square the square root to find V escape, and then V escape would turn out to be what? 2 GM1 over R, and then you take the square root of that, and then that's the equation right here. Right, and then we'll take a look at an example. An example with orbital speed and escape speed. So given that a planet orbits the sun with radius 100 kilometers with orbital speed 5 kilometers per second, 10 kilometers above the sun's surface, find the mass of the sun. Well, obviously these numbers aren't really that realistic, but let's do it anyway. So the orbital speed, what is the formula for orbital speed as well? It's just root gm over r, right? Where this mass is the mass of the sun. And then is equal to 5 kilometers per second, so 5,000, right? Accounting for units. And then we're given this radius, right? So, and we have to be careful here because the radius of the sun is 100k, and then we're 10k above that, so this would just be 110 kilometers, right? And so we're just trying to find this mass of the sun, right? So let's do that, right? So if we square both sides, we get 25 times 10 to the 6th, right? Meters per second is equal to g times the mass of the sun over the radius, which is 110,000, right? So if we multiply both sides, this becomes, but by 110,000, this becomes 275, I think, times 10 to the 10 is equal to g times mass of the sun, and then just divide both sides by g, and then the mass of the sun becomes 275 times 10 to the 10th over g. And then obviously you could just plug in the actual value for g, and then you get the real mass of the sun, but I'll leave that up to you. And it says find the v escape speed of the sun, right? So we have to be careful here because we can't just use the same equation for this and you know multiply by 4 or something, right? Because, well, this radius would be different, right? So find the v escape speed. So what is v escape speed? That's root 2 gm, right, ms over the radius of the sun, right? And then that's equal to the escape speed, right? Nice and nice. And then that would equal what? Root 2g times, we found the mass of the sun over there, which was 275 times 10 to the 10 over g, and happily this g's cancel out, and then the radius of the sun, which was 10 to the 5th, right? And so you just calculate this out, and it becomes root, let's see, 550 times 10 to the 10 over 10 to the 5th, and then that would just make this into a 5, right? And then that just becomes root 5.5 times 10 to the sorry, times 10 to the 7th, right? Yeah, that's 10 to the 7th. And then you can just plug that into a calculator and find that, and that's just mostly calculations instead of real physics. Sorry. So moving on. Oh, thank you for watching the video. Be sure to like, subscribe, and look out for future uploads.